Electricity powers your home, but under the right conditions, it can turn air into something that melts steel. Watch this. A stream of light touches steel and it just disappears. Faster than your eye can register. Gone. Instantly. Not burned, not cut, not melted by fire. Gone. By air. Turned into plasma. And the next time you hold a piece of metal, any metal, you're holding something that was almost certainly plasma not long ago. By the end of this video, you will understand exactly how electricity makes that happen, and why it is responsible for building almost everything around you. There is also a reason this matters that most people never connect. It starts on a factory floor. It ends at the edge of humanity's most ambitious energy project in history. We will get there. Let's get into it. Add enough energy to a solid, it melts. Add more, it becomes gas. But if you keep going, the atoms themselves fall apart. Electrons get ripped free from their nuclei. You no longer have gas, you have a completely different category of matter. A hot, chaotic mix of ions and free electrons, moving independently, colliding constantly, radiating enormous energy. That is plasma. It's air in a completely different state. 99% of all ordinary visible matter in the universe is plasma. The sun, every star, lightning, the aurora borealis, all plasma. Plasma is what matter becomes when it has too much energy to hold its electrons. It is matter in its most energetic, most liberated form. For most of cosmic history, that is the default. Life on Earth is a quiet exception, a brief window in the universe's history where matter gets to stay solid, liquid and gaseous, where the violence of plasma is kept at a distance. Until humanity learned how to make it ourselves. You've probably seen a plasma cutter and thought that is just a fancy torch. It is not. What you are watching is matter changing state in real time. Electrons being stripped from atoms by force. A new category of matter appearing where there was only air a moment before. And plasma cutters are everywhere. People need to cut metal fast and clean. Shipyards, pipeline construction, automotive manufacturing. The reason they have displaced so many other cutting methods is not just speed. It is that plasma cuts any electrically conductive metal equally well, with almost no heat transferred to the surrounding material. For precision fabrication, that matters enormously. And here is what makes plasma matter for everything we're about to cover. It conducts electricity brilliantly because those free electrons create an extraordinarily efficient pathway for current to flow. And it responds to magnetic fields. It can be shaped, steered and controlled in ways ordinary gas cannot. That second detail is going to pay off later, twice. First inside the furnace, where it does something most people never expect. And again at the very end of this video, inside the most ambitious machine humanity has ever built. And there is something else happening inside that furnace that almost nobody talks about, including what makes graphite the only material that could possibly do this job. We will come back to both. Air feels empty. It isn't. It's packed with molecules, and under normal conditions their electrons are locked in place. That's why air doesn't conduct electricity, until it does. Apply enough voltage and the field accelerates the small number of free electrons that always exist in any gas, knocked loose by cosmic rays, natural radioactivity or thermal fluctuation. Those electrons collide with neutral air molecules, knocking more electrons loose. The number doubles with every generation of collisions. This is called an electron avalanche, a cascade of ionization that converts a good insulator into a conductor in microseconds. By the time it completes, you have a channel of fully ionized gas connecting your two electrodes. Current rushes through it. The current heats the plasma. The plasma expands. The channel stabilizes into what we call an arc. And the heat that results is where this story gets extraordinary. There are actually two different temperature zones happening inside an arc furnace simultaneously. At the point where the arc contacts the steel charge, the temperature runs between 3,000 and 6,000 degrees Celsius, 2 to 4 times what is needed to melt steel. But the plasma column itself, the core of the arc, the channel of fully ionized gas between the electrode tip and the charge, is a different environment entirely. At its core, temperatures can reach 20,000 degrees Celsius and beyond. The surface of the Sun sits at approximately 5,500 degrees Celsius. The plasma column generated inside a steel factory is hotter than the surface of the Sun. The surface, not the core. We will get to the core later, and when we do, the numbers get stranger. That plasma, directed, focused, and aimed at steel, is exactly what those cutting tools are using. Not a blade, not a flame. Physics. And that's the smallest version of this idea. When you scale this up, you do not just cut steel, you melt entire buildings' worth of steel in a single run. The RC, the plasma, the heat. This physics was always there. One man figured out what to do with it. It is 1900. The steel industry runs on blast furnaces, enormous structures that burn coke to generate the heat needed to smelt iron ore into steel. The process works. It has worked for centuries, but it is expensive, filthy, and completely dependent on coal. Paul Héroult was a French metallurgist who had already changed the world once. In 1886, at the age of 23, he co-invented the electrolytic process for producing aluminum. The reason aluminum went from being a precious metal, once more expensive than gold, to the material we wrap sandwiches in. Héroult understood electricity. He understood what it could do to matter. And when he looked at the electric arc, he did not see a torch. He saw a furnace. His first electric arc furnace, patented and first operated in 1900, melted steel using nothing but electricity and graphite electrodes. No coal, no coke, no combustion, just current, arc, plasma, heat. The steel industry resisted for decades. Then World War II arrived, and suddenly electric arc furnaces, because they could start in minutes, run on scrap and required no coal supply chain, were the only furnaces that could keep up. Factories ran around the clock. By the end of the war, the industry had built its entire recycling infrastructure around it. Today, electric arc furnaces produce roughly 70% of all steel in the United States. Now let's go inside. The electric arc furnace is a controlled lightning strike that you can aim. A massive furnace lined with heat-resistant ceramic. Above it, 3 graphite electrodes the size of telephone poles. The furnace is loaded with scrap steel. Old cars, demolished building frames, washing machines. In the United States, roughly 70% of all steel production runs on recycled scrap. The car you drive might be made from someone else's old car. The steel in a modern skyscraper might have been a cargo ship 50 years ago. A railroad before that. A bridge before that. The atoms don't know, they just change form. Steel doesn't wear out, it circulates. Same matter. Endlessly reborn in plasma. The roof closes, the electrodes lower. Power on. For most of human history, heat came from burning something. Inside this furnace, nothing is burning. The electrodes draw a 3-phase arc down to the scrap below. Plasma forms, the scrap begins to melt, not slowly, not gently, instantly, in the zones where that arc makes contact. Over time, the solid pile collapses into a pool of liquid steel, cleaned of impurities by a floating slag layer above it. Below, the arc keeps pushing. Think about what that actually means for a city. Every time a building comes down, its steel doesn't disappear, it goes back into the furnace. The United States alone recycles around 70 million tons of steel every year, more steel by weight than any other material. The energy cost of melting scrap is roughly a third of what it takes to produce steel from raw ore, and every ton recycled saves around 1.5 tons of carbon dioxide. The furnace isn't just a manufacturing tool, it's the infrastructure for a circular economy most people never think about. Stop! Before we go further, remember what I said about something the electrodes are doing that nobody talks about, and why graphite is the only material that could do this job. Here it is. The electrodes are consuming themselves. Graphite conducts electricity well enough to sustain the arc, survives temperatures that would destroy any metal, and when it does burn away, it burns cleanly. No contamination enters the steel below. New segments are threaded on continuously as the old ones disappear. The tool that creates the plasma is engineered to sacrifice itself so the steel doesn't have to. And now, the first Lorentz force payoff. Plasma responds to magnetic fields. The enormous currents running through the melt, hundreds of thousands of amperes, generate magnetic fields inside the liquid steel. Those fields interact with the current flowing through the melt and create physical forces on the liquid metal itself. Forces that push and stir and circulate the steel continuously throughout the melt. No pump, no paddle, no intervention of any kind. The physics stirs the steel for you. That's the Lorentz force, the same force that makes electric motors spin, that guides charged particles and accelerators. The same physics doing the job of a mechanical stirrer with zero moving parts. Remember it. It comes back. Temperature alone doesn't tell the whole story. The hottest gas flame you can produce, oxyacetylene, peaks around 3,500 degrees Celsius. A plasma arc starts getting interesting at 5,000 degrees Celsius. But even that comparison understates what's happening. Plasma delivers energy orders of magnitude more densely than any flame. Concentrated, directional, relentless. A flame spreads, it diffuses, it heats a volume. The plasma arc is a point source of extraordinary intensity. The energy goes exactly where you point it, at densities no combustion process can match. But there's something else happening that most people never hear about, and it might be the most interesting of all. When plasma contacts a cooler surface, the ions and free electrons at the boundary recombine. The ion captures a free electron and becomes a neutral atom again. This releases the ionization energy, the exact amount of energy originally required to strip that electron from the atom in the first place. Plasma doesn't just transfer heat, it also releases the stored energy that was inside it, the exact energy used to strip those electrons in the first place, right at the point of contact. Not extra energy appearing from nowhere, stored energy returned exactly where it's needed. Like a compressed spring releasing all at once the moment it touches the surface. Every time, without fail. Built into the physics, and this principle, plasma releasing the energy of its own creation at the point of contact, is the same class of idea set behind the most ambitious energy project humanity has ever attempted. Hold that thought, we're almost there. Look around you right now, whatever room you're in. The rebar in the walls, the frame of your car, the pipes under your city, the tools used to build the device you're watching this on. Almost certainly, plasma. Electric arc furnaces produce around 70% of all steel in the United States. Globally, hundreds of millions of tons of steel are born this way every year. Every single pore of liquid steel is plasma at work. The same physics operates across every scale we have found use for. The handheld cutter is just the smallest version. Ion drives push spacecraft across the solar system at 10 times the propellant efficiency of chemical rockets, bleeding plasma out the back at controlled speed. Cold plasma, generated at near room temperature using short energy pulses, kills antibiotic-resistant bacteria on contact and accelerates wound healing. It is being trialled in surgery, dentistry and cancer treatment. It is the same ionization physics that cuts steel at 20,000 degrees, and yet it operates so gently it can treat human tissue. The same physics, 20,000 degrees in one room, a surgeon's tool in the next. We did not invent this, we just figured out how to aim it, and then there is ITER. In southern France, inside a building the size of an aircraft hangar, humanity is assembling the most complex machine ever built. It is called ITER, the International Thermonuclear Experimental Reactor. 7 members, the European Union, China, India, Japan, South Korea, Russia and the United States, are building it together. The price tag runs to tens of billions of dollars. The timeline spans decades. The ambition behind it is almost impossible to state plainly without sounding like science fiction. ITER is attempting to recreate the sun, not metaphorically, not approximately. The same process, hydrogen nuclei colliding at extreme speed, fusing together, releasing energy, contained inside a machine on Earth. And the thing that makes it possible is plasma. Here is the problem ITER is solving. Conventional energy sources are limited by what is in the fuel. ITER's fuel is hydrogen isotopes, deuterium extracted from seawater. There is enough in the world's oceans to power human civilization for hundreds of millions of years. When two hydrogen nuclei fuse, a small amount of mass converts directly into energy. The yield is roughly 4 million times greater per unit of fuel than burning coal. The byproduct is helium. No carbon, no long-lived radioactive waste. The fuel supply is, effectively, the ocean. This is the bet. But here is why it is so extraordinarily difficult and why plasma is the only possible answer. For fusion to occur, hydrogen nuclei have to get close enough to fuse. The problem is that they are both positively charged and they repel each other. To overcome that electromagnetic barrier, they have to be moving so fast, have so much kinetic energy that they can punch through it. The temperature required is 150 million degrees Celsius. The core of the Sun, the deep interior where fusion actually happens, sits at approximately 15 million degrees Celsius. ITER's plasma must be 10 times hotter than the core of the Sun. The Sun achieves fusion through gravity, the mass of an entire star crushing hydrogen inward with such force that even at 15 million degrees, the density is high enough for nuclei to fuse. We cannot build something with the mass of a star, so instead we compensate with temperature, 10 times hotter, fast enough that even at lower density the nuclei fuse on collision. At 150 million degrees, nothing can contain plasma by contact. Every known solid, metal, ceramic, all of it vaporizes instantly. The plasma cannot touch the walls of the vessel, and this is where the Lorentz force comes back. The same physics that stirs liquid steel in a factory applied at a completely different scale is how ITER contains its plasma. ITER uses a tokamak, a donut-shaped magnetic cage. Enormously powerful superconducting magnets cooled to near absolute zero generate fields that confine the plasma in a helical path inside the vessel, touching nothing. The plasma at 150 million degrees is held inside a magnetic bottle. The superconducting coils operate at minus 269 degrees Celsius, 4 degrees from absolute zero. And just a few meters away, separated by vacuum and magnetic fields, matter exists at 150 million degrees. The temperature difference between the coils and the plasma may be the most extreme thermal contrast ever deliberately created by human hands. This is the central trick. Without plasma's response to magnetic fields, fusion energy is physically impossible to pursue. If the plasma touches the wall, the machine is destroyed in milliseconds. The cage is not optional, it is the entire premise. When ITER achieves its design goal, currently projected for the 2040s, a timeline that has evolved as the engineering challenges have grown clearer, it will produce 500 megawatts of fusion power from 50 megawatts of input. A tenfold return. The plasma will sustain a net energy gain far exceeding what is put in for hundreds of seconds at a time. This is called a burning plasma, the point where fusion products heat the plasma faster than it loses energy. True ignition, a fully self-sustaining plasma needing no external heating at all, is the goal of the reactors that come after ITER. No energy project in human history has attempted this. It is the same phenomenon, electricity turning matter into plasma. Scaled from a handheld cutting tool to a furnace full of scrap to a machine attempting to recreate at the core of a star. Before we close, I want to see if you have been following along. There is a specific question in this video that has a complete answer if you are paying attention. In the comments, explain why graphite works as an electrode material in an arc furnace. What properties make it suitable? Temperature tolerance, conductivity, what happens to the electrodes over time, and crucially, why the way it fails actually matters. I'll pin the best explanation. No looking it up. If you made it this far into a video about plasma physics and industrial metallurgy, you're probably the kind of person who finds the hidden physics of the world genuinely interesting. That's what this channel is. Subscribe if that's your thing. The electric arc furnace has been around since 1900. For over 100 years, it has been turning electricity and scrap metal into the structural backbone of civilization. The The steel industry still accounts for roughly 7 to 8% of global carbon emissions, and the most promising near-term path forward runs through the same physics. Hybrit in Sweden has already delivered fossil-free steel to Volvo, using hydrogen in place of coal, with hydrogen reacting with iron ore to produce water instead of carbon dioxide. Researchers are developing hydrogen plasma reduction next, using the same arc and the same furnace, pointed directly at decarbonising steel. The machine Herald invented in 1900 is still evolving, and if ITER works, if a burning plasma is sustained, if the engineering of subsequent generations of reactors is solved, then the long arc of this story closes. The same phenomenon that Herald harnessed in 1900 to melt scrap metal in a ceramic bowl, the same ionized matter we generate every day inside factories, that same plasma becomes the mechanism by which humanity powers itself. Not by burning the planet's stored energy, by replicating the process that powers the star we orbit. We started with cutting sheet metal, we are aiming at the sun.